This is an example of doing a regression t-test of the slope as well as computing a confidence interval for the slope. So what we have is we have data from, I guess, a study of some type where they looked at the average monthly temperature, and we're asking, as it increases, what happens to the electrical usage in kilowatt hours. So obviously it looks like there's a downward trend. We're given the raw data. We're given the computer printout, so we have most of the computations done for us. We have a scatter plot, a residual plot, a scatter plot, a residual plot of the residuals, obviously, and then a histogram of the residuals. So the question is there evidence of an association between average monthly temperature and electrical usage? That's what we want to do, and then do a confidence interval. So I went ahead and wrote out the hypotheses statement. So the null hypotheses would be that there's no association. Okay, and then there we would say that beta 1, the slope of the line that goes through the entire population, is 0. Okay, and then the alternative, what we want to prove, is that there is an association. So here we would say that beta 1 is not equal to 0. That's kind of what the question is asking. If you say, in this particular case, less than 0, that's probably okay as well, because there is sort of a dramatic decline in electrical usage. Okay, so let's look at the conditions. The straight enough condition is where it's the first thing we have to check. And what we look at the scatter plot, and of course we're kind of biased right now by this line that they put through, but typically you don't have the line yet. So you look at the scatter plot and sort of justify that it makes sense to put a line through it so we can obtain the residuals. So here we're just going to say something as simple as the association appears to be linear. Okay, we're not going to go too much further than that. Now, an independence assumption. There we need to have a random sample and a representative sample, but we have to go further since we're looking at two variables. We want to make sure that we have random scatter in the residual plot. So there's only 12 points. It would be nice if we had a couple more right there, but we don't. So, but in general, I don't really see a pattern. I don't see a curvature pattern, like something that it kind of comes down, but then, you know, these points are here, so it's kind of hard to say it comes back up. So anyway, I don't see any reason to say that it doesn't have random scatter. So the residual plot shows random scatter. Okay, now the equal variance condition. What we're looking for there is, what we'd like to say is that the variance is about the same. Okay, and it doesn't look too bad. These 2 points are sort of the same distance, sort of as this point here. It would be nice to have a couple more points, but given that we have such a small sample size, it looks okay. So we're going to say the residual plot shows a fairly uniform spread. Okay? Now the last thing we want to do is we want to look at the residuals again, but we'd like to make sure that the residual the histogram of the residuals is unimodal and roughly symmetric, and it does look like that's the case. Okay, again, we'd like to have more data to see it fill out, and then there's no outliers. So the histogram of the residuals appears to be unimodal and symmetric. Okay, so we're good to go. The conditions are met, so we will proceed with a regression t-test for the slope using a student's t model with n minus 2 degrees of freedom. So that's going to be 10. Okay, so we've introduced the model. So we actually are using the term model in a couple places. So I want to just discuss that quickly if I can. So first, we have a linear regression model. That's the straight line that we put through the scatter plot. That's y hat equals b0 plus b1 times x. And it's used to approximate the population model. Okay, so that's a linear regression model. Here we have a model of the sampling distribution of the slope B1. Okay, so our hypotheses, our null hypotheses was that it was 0. Okay, so our center is 0, so we expect it to land in here. So we can use the calculate the t-value to see how many standard deviations away it is. So we take the test statistics, the slope minus the hypothesized value, and divide by the standard error of the slope, just like a one sample t-test. So this data comes from, here's the y-intercept, here's the slope, and here's the standard error of the slope. And let's see, the t-value is negative 10.2. So we can kind of do this all at once. So this is going to be negative, what was it? Now I forgot. 50. Negative 50.9 minus 0 divided by 4.98. Because I could throw in a 0 there. And that comes out to be negative 10.2 standard deviations away. So that's like 1, 2, 3, 4, 5. So way out here somewhere. Okay, so the p-value is equal to, and in my case, 2 times the probability that t is less than negative 10.2. Okay, and we're going to be able to get that from the computer output. Here's the p-value right there. It's going to be less than 0.0001. Okay, so there's not much we have to do to the model here to draw it out. We have everything. So we can say that the p-value is small, so we reject HO. There is strong evidence that as average monthly temperature increases, the electrical use decreases. Okay? So the question is, by how much? All right? I guess I say decreases. I could have said that there's strong evidence that that they are associated. But I'm going to say that in this case that they decrease, and then I'm going to create a confidence interval. So remember, that's an estimate plus or minus the margin of error. Okay, so the estimate is our slope. Okay, so we're going to put a bound around the slope. Essentially what we're doing is we have this slope, but if we randomly sample many times, we may get slightly different slopes. Okay, so we want to say, well, how much does that slope vary? Okay, so plus or minus t star of 10 times the standard error of the slope. Okay, so that just becomes negative 50.9 plus or minus, and I get, let's see, 2.228 times the standard error. We already found that on the computer printout. Okay, so our confidence interval becomes, I get negative 6100 to negative 39.81. All right, so how do we interpret this? So there's a couple ways of doing it, but let's just say I am 95% confident that let's see, that for each average temperature monthly temperature increase of 1 degree Fahrenheit, the electrical usage decreases by between 61.0 to, what was it, 39.8 let's see, kilowatt hours. Okay, so you have to think through interpreting the slope, especially when you're specifying a range. So there's a question here, some follow-on questions. What's the model? So we could say kilowatt hours, put a hat on it, equals the y-intercept 3898.20 minus 50.90 times the average temp. So that would be our model. Okay, so what's the strength of the model? Well, R is the square root of R squared. And let's see. I think that's going to turn out to be so that's the square root of where is it? Here's R squared right here. So 91.3% or 0.913. So the square root of that, I believe it comes out to be 955. So it's close, very close to 1. So we say we have a strong positive, oh no, negative linear correlation. We don't have to, we can use correlation now because we've done all these tests. So how useful is the model? Well, that's R squared. So if R squared is 91.3%, then we would say that 91.3% of the variability of electrical usage is explained by the variability in average monthly temperature. Okay? So what's the expected value? So here we would just do it for an average monthly temperature of 55. So here we would just say KWH is equal to 3898.20 minus 50.90 times 55. And I get 1098.5. Okay, so I probably should say something like, according to the model, we expect, and then just keep going, a house or an average, a house would need this many kilowatt hours if the average monthly temperature was 55. So how far off are we? So that what that's asking is, what's the residual? So the residual is equal to the observed minus the expected. Okay, and sometimes we say E. So the observed value is up here. If we go up to the raw data, here's 55, so it would be 878 kilowatt hours. So 878, and we're going to subtract off what we just computed, 1098.5. So I get about negative 221. Okay, so for this observed value, of 55 temperature, the model overestimates because the model is bigger than the observed, so it overestimates. The electrical usage. Okay, so long problem. That last part is kind of review on how to use a model. But you can see there's a lot of steps here, but it's pretty straightforward and follows pretty much the same logic as a regular hypothesis test. So good luck.